In the previous lecture, we have looked at how we obtain the divergence theorem from the Green's theorem. So now we are going to look at the meaning of divergence, and you will see that the divergence is applied in many physics problems. For example, the flow of water, the flow of particles, and so on. So let's look at the following slide. So in this slide, I have plotted the x, y, z axis. This is the x-axis, y-axis, and the z-axis. And now we are going to consider imaginary rectangle over here. Okay, and since this is the x-axis, so if you go from this point to this point, this is along the x-axis, and therefore this is dx. On the other hand, if you go along this axis, this is going to be dy, and here this is going to be dz. Now let's remove the axis in order to clear our diagram a little bit. And now we want to consider a stream of particles or water, for example, that moves from, say, one side on the left hand side here to the right. And this is done under the vector field. So let's assume that the flow of water, and this flow of water is represented by a vector which is given like this. So this is my I component, J component, K component, and Vx, Vy, Vz is a scalar quantity. Now let's look at the area bounded by this rectangle over here. These two rectangles, squares I mean, sorry, and the area of this square, let's say this square here, is going to be equals to dy dz. So in case if you're asking why dy dz, you just have to recall that the area for a square is going to be a multiplication of the length here and this length. So in this case, this is dy and this is dz, and therefore you have an area which is dy dz. So now let's look at the flow of water that goes from this side towards the into the rectangle, and then coming out of this rectangle. And since the flow is along the x-axis, so remember this is the x-axis, and we can write the amount of the flow in this axis to be equals to a dot product between the vector field and the I. And this is going to be equals to Vx. So now the amount of flow at the surface. So let's look at the left surface here. So the amount of flow in this surface is going to be equals to Vx1, because this is the amount of flow, multiplied by the area, which is dy dz. So the rate of flow across the surface is given by this amount. So let's now look on the right hand side, and we will see that the amount of flow is going to be equals to Vx again, but now we put the subscript 2 in order to differentiate between the amount that comes out from the right hand side and the amount that comes in from the left hand side. So here the amount that comes out of the surface is going to be Vx2 subscript 2 times dy dz. So the net flow across the x direction. So the net flow means how much that actually goes through this rectangle or along this x-axis. Is going to be a difference between Vx2 minus Vx1. So the amount here, Vx2 minus Vx1, that comes in, and you multiply it with the area, which is dy dz. And then you can write this Vx2 minus Vx1 as a difference of Vx divided by the difference in x, right? And if the difference is very small, if the difference in the dx, the delta x is very small, then you can write it in terms of a partial derivative, and therefore you have this form. Right? So basically, here we see that the net flow from the left to the right is given by partial derivative of Vx with respect to x times dx dy dz. So what about the other direction? So let's look at along the z direction. So assume that the particles or the water is going from the top to the bottom. So now this is our effective surface area, and this surface area, the area is given by dx dy, because this is dx and this is dy. And we have the same form from before, and the net flow now, the net flow from the top to the bottom is going to be a partial derivative of Vz with respect to z multiplied by the z dx dy. So in this case, this is the area and this is the total net flow. So on the other hand, along the y direction, we have an area which is given by dz multiplied by dx, right? So this is a effective surface area, and the net flow from the not the top to the bottom, but now from the front to the back, is going to be equals to partial derivative of Vy divided by with respect to y multiplied by dy dx dz. So if you now with sum all these contributions, and then you will see that I can write it like this: a partial derivative with respect to x, y, z multiplied by basically the volume dx dy dz. And this can be written in terms of a dot product if you can see the pattern, because this is my divergence basically. So I have I partial derivative with respect to x, y, z, dot product with the vector field, and this is in a short form written like this. So now if you divide both sides with the dx dy dz, and you have a very simple form like this, right? So it means now you have a rectangle like this, and if the change in the x, y, z is very small, that is, you make it into a very small up to a particle point size, okay, and you will see that basically this tells you about the rate of loss per unit volume. So just now we have looked at the meaning of divergence, which tells you about the net loss of a certain quantity per unit volume, right? So now let's look at the example of a flow of water in a tube. So let's take for example a tube which has a length, in this case Vt, and the water flowing from the left to the right. Here we have V over here, capital V, which denote that this is a vector, and this is equals to the density of the water, rho, multiplied by V, and this is a vector as well. Basically it's showing that this is the vector along this direction. So this scalar V over here, Vt, this V is a scalar quantity of this vector V with the arrow. And in this tube, the area over here that is traversed by the water is denoted as A prime. So now when we want to find out what is the amount of water that goes through this tube for this area and this length, we have to multiply the length of this and the area of this. So you have Vt A prime and the density of the water. So basically when you do this, you will get the amount of water going through this region. So now let's take the case where we have a region where it is slightly bent, and we can define, in this case, in the area which is not bent over here, we can have a normal vector, and over here where we have a slight bend, we can also have another unit vector which is denoted by n with the arrow, and it makes the angle theta with the region where it is not bent over here. Okay, So this is A prime before the band, and after the band the area is denoted as A. So the relation between A prime and A can be written simply by A prime equals to A cos theta, because here you can see this is my A prime. So A cos theta, which is, I just have to tilt a little bit, and this will be equals to A prime. So now the amount of water that flows through the tube is going to be from here, this is before the band, and I will put in A cos theta over here so that I have this equation. So now we look at the region where there is a slight bend, and here we can also represent a unit vector which is normal to the surface by NA prime. This is for the surface which is not bent, and for the surface which is banded, we can have also a unit vector normal to the surface given by NA. So now the relation between the two is going to look the same as the one you have for the area. So here you have an NA prime, which is the unit vector in the case where there is no band, and this is equals to NA cos theta. So now let's go back to the amount of water flow. So here, this is the equation that we've seen in the previous slide, and we can rearrange it a little bit so that you have rho v over here, and then you have T and A cos theta. So now in the case where you have a unit volume and unit time, so you replace T by 1 and A by 1, and you have this expression, and you can write that this as a scalar or the vector v that we have seen just now. Okay, so just to be careful, this v is a scalar quantity, and this v with a head is a vector, but this is the modulus of it, the length of it. So here we can go to the next line in this expression, because my NA is a unit vector, so this is equals to 1. And if you remember from the definition of the dot product, you will notice that this is exactly the vector v dot with the unit vector NA. So here this tells you that the amount of water that goes through a tube in a certain region is basically the vector field dot with the unit vector normal to the surface. So let's say you have a tube over here, and then you want to find how much water goes through this surface, this region. You have to take the unit vector that represents the flow of the water, not the unit vector, but rather the field vector that represents the flow of the water, and then you dot with the unit vector normal to the surface. So in the case where you have a banded region over here, you will still have to take the v, but you take the dot product of the v with the unit vector and a. Alright, so basically here is an example of the application of divergence in the case of a water flow, but this is also nice to bring into mind that this is not limited to tube per se. It can be in any case, even for example in the case of blood flow through the blood vessel.